Yes, sir.
Right. So we'll continue with this discussion about creating a perspective for use of probability in AI, NLP, machine learning, especially with the focus on natural language processing. So we're slowly progressing towards establishing the central limit theorem, which allows us to uh, use the instruments of normal distribution, whatever be the underlying distribution for the data. Okay, so that's a strong statement. Whatever be the underlying distribution on the data for particular random variables, we can still make use of the properties of normal distribution because of central limit theorem. Now, we are trying to create a story through the observation that ambiguity is inevitable for natural language processing. At every stage of NLP, we have to deal with ambiguity. Now, here we saw that since ambiguity is the main problem, the instruments of probability and the data uh, made their appearance. So it was not, though it was not obvious at the time, and in fact, a lot of Puritans laughed at this possibility of use of data for doing language analysis. On hindsight, when you look at the history, it seemed inevitable that this is what had to happen. You had to bring in probability, a framework to manage uncertainty, ambiguity. This had to happen. I mean, what else could you really do? Because the other name of natural language processing is ambiguity. So deal with uncertainty, you have to bring in the framework of probability. And on hindsight, it seems this had to happen. So I mentioned this paper in 1988, which showed how to do part-of-speech tagging using statistical optimization. And hidden Markov model with Viterbi was a spectacular success for doing part-of-speech tagging and apparently thoroughly linguistic task. Then machine translation saw a paradigm shift through this 1990 paper from IBM, which showed how to use expectation maximization for word alignment, and from word alignment, how you could go to phrase alignment, tree alignment, chunk alignment, and so on. But the foundational point was alignment and alignment probability. Okay, so these things were paradigm shifters, and it is inevitable that they had to happen. And then another milestone came in 2010 to 16 range, where slowly neural networks started coming into natural language processing. And a spectacular success again was obtained through NMT, neural machine translation. And this is the paper which is really the milestone development in machine translation. Google's neural machine translation system bridging the gap between human and machine translation. It showed that as data increases, the accuracy curve very rapidly crosses over statistical machine translation. And again, after some time, I think we'll get an insight into why this also had to happen, because the amount of data crossed a particular threshold so that non-parametric estimation became possible. So what did neural computation bring? It reduced burden on human thinking still further. And the oft-used expression is end-to-end system, quite abused also, that just give data to a machine and you'll get your work done without any thinking, without any theory building, without any insight at all. So neural network started changing the thinking and the world scenario by saying that the burden on human thinking will reduce and data will shoulder more and more responsibility. And this is the so-called non-parametric estimation. A large neural network would have a lot of weights and threshold values, and they would get fixed through training. So that is what neural computation brought in. So neural network is very old, older than symbolic AI. Now I'll illustrate this point with an example. So there are two English sentences, 3 rabbits and rabbits of Grenoble. The corresponding French sentences are Troya Lapin and Lapin de Grenoble. So this is a parallel corpus. 3 rabbits, Troya Lapin, and rabbits of Grenoble, Lapin de Grenoble. They call Grenoble, the French people. So can somebody verify that you're looking at the rabbit example on the screen?
Yes, sir.
Yeah?
Yes, sir.
Yeah, okay. So, so now imagine yourself to be a machine which is looking at the parallel data and trying to establish correspondences. What does 3 correspond to? What does rabbits correspond to? And what does off correspond to and Grenoble correspond to? So now if you have no other prior knowledge and you have no access to morphology, part of speech tagging, parsing, nothing, absolutely no NLP processing, then if you look at the pictures of these sentences, I use the word pictures to share this, to say that you are just processing patterns in front of you on the screen. So you can see that rabbits are a BBITS. This string appears twice. And lapin, LAPINS, on the French side also appears twice. So maybe this is the clue to establishing a correspondence. This rabbits occurring twice, lapin occurring twice, gives me a clue that most probably rabbits and lapin, they correspond. So this is a purely count-based thinking, and this count-based thinking is at the heart of, as you know, probability computation. The frequentist approach to probability is based on counts. So no semantic information, no pragmatic information, no parsing, morphology, nothing. Just looking at the patterns and establishing correspondences. So this, by the way, was made possible by this seminal work from IBM in 1990 on word alignments. So this is IBM model number 1. So initially we begin with uniform probability. We have no knowledge, completely uncertain world, and you cannot seize any advantage of any count or correspondences. So the 3 rabbits of Grenoble are the English words on the columns, and Troya Lapin de Grenoble, this is on the row. Now Troya corresponds to 3 rabbits of Grenoble with equal probability. I have no knowledge, so I have to give same probability to this correspondence. Troya corresponds to 3, 1/4 probability, rabbits 1/4, off 1/4, Grenoble 1/4. So in absence of any other information, this is the best you can do. And that has the maximum possible uncertainty and entropy. So I'm interested in finally discovering the exact correspondences so that this Lapa rabbit's correspondence should become the winner. Okay, Lapa can only correspond to rabbits. Other probability values should get depressed, and Lapa rabbit's probability value should get enhanced. So the probability mass function, which is on the Lapa row, initially is a straight line, but gradually it will begin to change shape and will peak at this cell, Lapa rabbit cell. Okay, and see that our starting point is probability. We start with probability. This is the instrument we have to use, and there is no other way really better than probability to establish this correspondence. Example-based machine translation tried to extract this kind of correspondences, but it was not well principled. So I discussed this in chapter 6 of my book on machine translation, why example-based machine translation and statistical machine translation, though both of them were data-driven, the statistical machine translation seized the advantage of probabilistic framework. Example-based machine translation, on the way, tried to seize analogy, tried to exploit the notion of analogy, but really did not go very far, okay, because it was not principled. So we start with this kind of initialization of probability values, and then through a series of expectation maximization steps, okay, continuous back and forth computation of expectation and maximization, we come to a stage where you can see Lapa rabbit's correspondence probability has increased a lot to 85 by 144. Other probabilities are getting depressed. So this is an iterative algorithm, EM algorithm, based on probability. And after some time, there is a convergence. Actually, it maximizes the likelihood of the observation. The observation is the parallel corpora. So as we go forward, we'll have occasion to use maximum likelihood estimate for parallel corpus for statistical machine translation. So this is what statistical machine translation brought into NLP. This was a huge computation, a huge contribution if you look at the history of NLP and machine translation. Completely paradigm changing contribution, and very, very influential. So here, what is happening is that it is fixing these parameters. So probability of Lapa given rabbits or probability of rabbits given Lapa is a parameter of the situation. So it is a parameter of the distribution which is manifested in the maximum likelihood expression of the parallel corpus. Okay, so these notions we'll have to make more concrete as to what do we mean by the probability of the observation. In this case, the observation is parallel corpus, and we assume there is an underlying probability distribution. That probability distribution's parameters are these word alignment probabilities. Okay, so we are doing essentially parametric estimation in statistical machine translation. So here the burden is on human beings still. Okay, we have to create a sensible likelihood expression. What did neural machine translation do? It introduced the encoder-decoder framework. So I input Troya Lapa the Grenoble, and it passes through encoder, becomes a vector representation. Of course, each word is a vector representation. The whole sentence becomes a vector representation. And then it passes through the decoder, that vector representation, and gets converted into 3 rabbits of Grenoble, the English sentence. So this is a French to English machine translation system. For the new sentence Troya Lapa di Grenoble, it becomes 3 rabbits of Grenoble through encoding decoding process. So it is not obvious where the alignment probabilities are. Okay, the correspondence of 3 to Troya, rabbits to Lapa, off to the Grenoble to Grenoble. It is not very obvious where these alignments are, but it is extremely obvious in statistical machine translation, where the phrase table gives you the word alignment probabilities. Now, to an extent, these alignment can be traced to attention, but my close, study of attention and encoder-decoder framework tells me that this correspondence is not as clear and as crisp as in statistical machine translation. You can trace these alignments in the phrase table. You cannot trace these alignments in the encoder-decoder network so cleanly. It is a distributed representation. So what gets fixed through training are the weights of this neural network, namely the encoder-decoder. And it delivers by converting the French input sentence to English output sentence through the process of encoding decoding. So this preliminary discussion, before we delve into more specific things, was to sensitize us to where probability is playing its role. Where is probability inevitable? Okay? And it seems that when we deal with parallel corpus in data-driven machine translation, we have to invoke probability. And though neural network is doing non-parametric estimation, the weight values get fixed from the data. The output layer, the ultimate output layer, actually does softmax computation, which is again based on probability. So our investigation into the inevitability of probability in NLP is substantiated by another situation, namely machine translation. So we proceed and go back to our previous lectures discussion, namely probabilistic parsing. So this is another NLP situation where we had to invoke probability for a systematic treatment of ambiguity during parsing stage. That is structural ambiguity. I saw the boy with a telescope as structural ambiguity. Who has the telescope? And that decides also the shape of the parse tree. Now, we were looking at probabilistic context-free grammar. And in particular, we're discussing the 3 ways in which a noun phrase can be formed: through determiner and noun, or through plural noun, or noun phrase followed by preposition phrase. The boy with a telescope. So from the corpus, we got these probability values. Noun phrase goes to determiner noun with probability 0.5, going to plural 0.3 probability, going to noun phrase, preposition phrase combination 0.2 probability. Now, this is from the sample or the data, which is the tree bank corpus. But we emphasized this last time that based on these data observation, data statistics, we make a claim about the language property. We are saying that English noun phrases, 50% of them are determiner noun combination. So this is a very big leap of generalization from sample of data to the whole language property. Okay? This is a tremendous leap of generalization. Now we must be confident that this generalization is really valid. So we saw that this 50% probability for noun phrases being composed of determiner and noun has this interesting behavior if we draw different samples and record the probabilities. We find that the probability value peaks in the range of 40 to 60. Noun phrase consisting of 80 to 90% times determiner and noun is very rare. That count false. And noun phrase consisting of determiner and noun only 10% of the cases, that count also false. So we see that the probability mass is concentrated in the range of 40 to 60. And this happens as we keep on recording the observations with more and more samples. The other thing we can do is that we can go on increasing the corpus size. And there we see that there is a kind of saturating behavior at the value of 0.5. I should have written 0.5 here. So probability of NP going to DTNN becoming 0.5, that begins to manifest as the corpus size increases. Now, interesting thing is this chart and this curve, saturating curve, are interconvertible. You can derive one from the other. If you, on the y-axis, which is the probability value, if you mark off segments 0 to 10, 10 to 20, 20 to 30, and so on, and then record your observations looking at the curve, then you can come to this kind of bell-shaped chart. So these two curves are interconvertible, and this is only stating another well-known fact from statistics, which is also very glorified actually, that law of large number and central limit theorem are law of large numbers and central limit theorem are two sides of the same coin. Okay. So now this is another perspective which we got, but we are curious to know what is the behavior of noun phrase going to DTNN. What kind of distribution does it follow in the underlying data? So here we would like to draw an analogy with another very famous probabilistic situation, throwing of dice. The random variable is the outcome of throwing a dice. There are 6 outcomes. In Bernoulli trial, there are 2 outcomes. This is what is called a multi-Nolli trial. There are 6 outcomes. And the number of outcomes follows the multinomial distribution. Okay, not binomial. Binomial happens for Bernoulli. This when the number of outcomes is more than 2, it follows multinomial distribution. And there is a very clean formula for this. The probability that 1 appears n1 times, 2 appears n2 times, and so on, 6 appears n6 times out of a trial of n throws of the dice. That is given by n factorial by n1 factorial, n2 factorial, up to n6 factorial, p1 to the power n1, p1 to the power n2, p6 to the power n6. A very elegant expression. And this gives you the probability of how many times you can expect to see 1, 2, 3, etc. So that question is very similar to the number of times noun phrase appears as DTNN. If we are able to stretch our imagination a bit and do a bit of analogical thinking, we see clear correspondence between the dice throwing and asking in how many different ways noun phrase can be formed in English language. So that's very interesting, right? That there is a correspondence between throwing of dice and asking in how many ways noun phrase can be formed in English language. So can somebody verify you're looking at the dice throwing expression? Multinomial probability. Yes. Okay. So this is the multinomial distribution. And if you if you use this distribution to maximize the probability of observation, if there are n1 ones, n2 twos, and n6 six out of n trials, then by maximizing the likelihood of the observation, you can come to the conclusion that the probability P1 of 1 coming in a throw of the dice, 2 coming in a throw of the dice, is nothing but n1 by n, n2 by n, n6 by n. Okay, so this comes from maximizing the likelihood expression, which is a very powerful tool based on probability. So this is the underlying distribution for throwing of dice. It's exactly similar underlying distribution for noun phrase composition. Okay, so I record this analogy between dice throwing and the NP rule. So in language, the random experiment is observing the language phenomenon. In particular, in the specific case we are discussing, we are observing the language phenomenon of noun phrase. So noun phrase is a language phenomenon. Nouns are language constructs. Nouns are language phenomena. Okay, so some unseen power gave us language. Okay, a means of communication, and building blocks in that instrument of communication were noun, verbs, adjective, adverbs, and so on. Things and actions, nouns and verbs, things qualified by adjectives, actions qualified by adverbs. So somebody gave us this very powerful framework, the language framework. And there is a huge amount of unknowability in this. Okay, like many mysteries of nature, language is also deep and mysterious. Okay, what is the percentage of noun in the language? What is the percentage of adverbs in the language? Proportion. Those questions are not easily answered. They are not completely answerable also. There is always uncertainty for them, and therefore we invoke probability. So the random experiment here is observing the language, and since we cannot see the whole boundary of language at any point of time, language is an evolving entity and extremely large, we have to invoke probability and we have to invoke random experiments. So the analogy is random experiment with respect to language phenomena is analogous to random experiment with respect to throwing of dice. You throw a dice and observe what is happening. You pick up corpus and observe in how many ways noun phrase is created. NP rule has 3 outcomes as specified in the grammar. Dice throwing has 6 outcomes. Probability of each RHS of the NP rule is the property of the language. Probability of each outcome is a property of the dice. If the probability of obtaining 1 when I throw a dice is 0.7, then it is a property of the dice itself. And this we can estimate only by observing the dice, by throwing the dice many times. There is no other way. Can you really perform an X-ray on the dice? Can you pass it through an computer-aided tomography or some kind of X-ray crystallography, etc., etc.? You open up the dice. Okay, you look at each of its molecules. But can you give the probability of obtaining 2? No, probability is a macro observation. And it is not easy to go to that macro observation by looking at each and every molecule of the dice. Maybe it is impossible. Similarly, the probability of noun phrase going to determiner a noun, can you really get to that value by looking at each and every character, each and every phrase and word? That's a very, very stupendous task. Okay. Instead, you look at the samples and see how many times you get noun phrase consisting of determiner and noun. So by observation of language corpora annotated, we try to guess the properties as close as possible to reality. Property means noun phrase and how it is created, constructed. By observation, we try to guess the properties of the dice as close as possible to reality. So let us remember this. It is instructive to draw analogy between language phenomena and very standard classical probability experiments, throwing of coin, throwing of dice, okay, and so on. So here again, the underlying distribution is a multinomial for noun phrase, but here is the main bridge, which is linking the underlying distribution with normal distribution. Whatever with the distribution which noun phrase is following, the probability of noun phrase being composed of determinant and noun, that probability being 0.5 is a fact obtained from looking at a lot of data and looking at a lot of samples, which gives me a bell-shaped curve or a saturating curve for the probability value. And the moment I get the bell-shaped curve, I'm opening up the toolbox, which is the normal distribution. So when we do computation of parse tree probabilities and output as the parsing algorithm, output of the parsing algorithm as the tree with the highest probability, then essentially we are doing a product computation for the rule probabilities. So how we can take this product is because of various kinds of Markov independence assumptions. And we need confidence in these probability values. So we need to go into the techniques of probability, especially normal distribution. So the techniques we have learned are properties of standard normal variable. Any normal distribution variable can be converted into standard normal distribution variable by subtracting mean from the random variable, dividing it by the standard deviation. Now we have also learned how to compute the Z score, which is the area under the curve from minus infinity to small z. And that is learned, that is obtained from what is called the Z score table. So for Z value 1.96, we look at the row 1.9 and column 0.06. There we find a value of 0.9750. So this is the area under the standard normal curve from minus infinity to plus 1.96. And from there, we could also derive the 95% confidence interval. So this is a powerful technique we learned. And using this, we could find out how many cars simultaneously on the bridge will make it unsafe. So that was done by comparing the Z-score value for the tolerance of the bridge. And we solved this equation and got the number of cars to be 170. So if we allow more than 117 cars on the bridge, then in 100 out of 1000 cases, the bridge will break. So that we could find out by confidence, by interval estimate and making use of Z-score. So these two powerful techniques we learned. One is to read off the Z-score from the Z-score table and to be able to estimate the value of a quantity of interest by comparing two normal distributions. Okay. So that was discussed in last few lectures. Now we come to the central limit theorem. So the law of large number states that as n grows, the probability that xn is close to mu goes to 1. Mu is a value, and cross CLT central limit theorem says as n grows, the distribution of xn converges to normal distribution with mean as mu and standard deviation as sigma square by n. So can somebody say that you are looking at law of large number and central limit theorem? This is the screen.
Yes, sir. The crownic rule is
Yeah. It's right. Okay. So we would like to state and prove central limit theorem, which is going to be making its appearance again and again when we deal with data. So first we state and prove some lemma. If x1, x2 up to xn are n independent random variables, and if we have Sn as the sum of these n random variables, then it is known that expectation of Sn is sum of expectations. Okay, this can be proved from the first principle, from the definition of expectation, which is probability mass function multiplied by the value of the random variable and taking sum over all possible random variable, all possible values. And if it is a continuous distribution, then we have to integrate. And interestingly, the variance of Sn is again sum of variances. Okay, so you can see from the expectation expression that expectation is sign sensitive. It is sensitive to sign. Expectation of x1 minus x2 is expectation of x1 minus expectation of x2. But variance is sign insensitive. Variance of x1 minus x2 is variance of x1 plus variance of x2. So this is an important point, an important difference between variance and mean. And it will be interesting for us to get an intuition as to why this happens. Why is that? Why is it that mean is sign sensitive, whereas variance is not sign sensitive? Okay? So if some of you can think about this and give the intuition, it will be great. So variance form is defined as expectation of x minus the mean, okay, and square of that. Expectation of the random variable, its difference from the mean, and square of that. So Ex is nothing but the mean. So let's see where variance of x1 plus x2 going from first principles. Variance of x1 plus x2 is expectation of x1 plus x2 square minus expectation of x1 plus x2 whole square. Okay, so this is from the definition of variance. Definition of variance, as you see, is random variable minus the expectation of the random variable. So this is what we are doing. Now we apply algebra a plus b whole square, x1 square plus 2x1 x2 plus x2 square minus ex1 plus ex2 whole square. Now expectation distributes over the operator which is summation. Okay, so expectation of x1 plus expectation of x2 whole square, again you apply a plus b whole square, then expectation of x1 square plus 2 expectation of x1 into expectation of x2 plus ex2 square minus ex1 square plus 2 ex1 ex2 plus ex2 square. So now these 2 ex1 ex2 cancels from both expressions, and you are left with ex1 square minus ex1 whole square plus ex2 square minus ex2 whole square, which is variance of x1 plus x2. What about variance of x1 minus x2? Again, go from definition. Expectation of x1 minus x2 square minus expectation of x1 minus x2 whole square. Definition of variance. Again, apply a minus b whole square formula, and we have x1 square plus minus 2x1 x2 plus x2 square. Minus, again, expectation distributes over the negative sign, so ex1 minus ex2 square. Now apply a minus b whole square again for the second expression, and I find that 2 ex1 ex2 gets cancelled again, and I am left with ex1 square minus ex1 whole square plus ex2 square minus ex2 whole square. So variance of x1 plus x2. So variance of x1 minus x2 is variance of x1 plus variation of x2. So variance is sign insensitive. So this is a nice property of random variables, and it will be interesting to know intuitively why this is the case. So let's proceed. Now comes the central limit theorem, again called reminding ourselves that it is one of the epitomes of mathematical thinking applied to uncertainty. If x1, x2, x3, x up to xn be n independent random variables, each with mean mu and variance sigma square, and we compose Sn as the sum of these random variables, then Sn is normally distributed. This sum is normally distributed, provided n is large enough. So large enough is stated in the literature to be n greater than 30. Whatever be the underlying distribution, the sum of these n random variables, whose mean and standard deviation of course are same, is normally distributed. So this is the theorem part. And the other point is that its mean is n into mu, and variance is n sigma square. So the sum of variances, the variance of Sn is sum of variances, and mean of Sn is sum of means. Okay, mean of Sn is sum of means, mean of variances is sum of variances. So you can create a standard, you can create this Sn star, which is Sn minus n mu, mean subtracted, divided by standard deviation. And since Sn itself is normally distributed, this mean subtracted and divided by standard deviation is the standard normal distribution. It has mean 0 and standard deviation 1. So we would like to prove that Sn star, which is created this way, is a standard normal distribution. Okay, and that is the central limit theorem statement. So, and this has tremendous application when you try to use central limit theorem in our problems. So when we try to use it, let's say for natural language processing, and I want to be confident that the noun phrase goes to determiner and noun with probability 0.5. By observing lot of corpus, I want to be confident that this is indeed the case. Why does it happen? Okay, so please see the motivation behind looking at central limit theorem in close detail. Okay, coming back to central limit theorem again and again. We are in the 6th lecture, and we are going deeper and deeper into central limit theorem. Okay, sort of excluding any other consideration. We are trying to see the use of CLT for natural language processing. So we would like to prove that Sn star is standard normal distribution. First of all, convince yourself that this needs a proof. Okay, this we cannot take it as a definition, nor can we take it for granted. Okay, it needs a proof. So the proof is through a very powerful machinery in statistics called moment generating function. Maybe many of you have done statistics and probability course and would recall that you have seen these terms before. Moment generating function, central limit theorem, and so on. So for a random variable x, the moment generating function is defined as expectation of e to the power tx. Okay, what is the intuition? What is the motivation? We are coming to that in a few minutes. So moment generating function for a random variable x is expectation of e to the power tx, which is equal to e to the power txj fxj, j equal to 1 to n for a discrete distribution. So if x takes values x1, x2 up to xj with probabilities fx1, fx2 up to fxj, then by definition, the expectation of e to the power tx is e to the power txj, the value of the new random variable, multiplied by the probability of the controlling variable, fxj. And for continuous distribution, it will be minus infinity to plus infinity integration e to the power tx fx dx. Fx is a PDF for x. Okay, so moment generating function is again a tremendous contribution from probability statistics. Why so? There are many reasons. The first reason is the uniqueness theorem. If x and y are random variables having moment generating functions mxt and myt respectively, then x and y have the same probability distribution if and only if the moment generating functions are identical, if they're equal. So uniqueness theorem establishes correspondence between distribution and moment generating function. There is one-to-one correspondence. If for two random variables, the moment generating functions are equal, then their underlying distributions are also equal. So this is what we'll apply for proving the central limit theorem. We'll prove that for Sn star, which is x minus n mu divided by sigma root n, the moment generating function is same as the moment generating function of standard normal distribution. So that is the motivation for looking at uniqueness theorem. Now, there are other reasons why moment generating function is important. So moment generating function is expectation of e to the power tx. Do you, yes, Manthan is asking if the two moment generating functions are identical. Yes, if the two moment generating functions are identical, then the two random variables x and y have identical distribution also. So, so now why moment generating? Why this phrase moment generating? So we look at the definition of mxt. Okay, definition of mxt. It is expectation of e to the power tx. Now e to the power tx can be expanded as 1 plus tx plus t square x square by 2 factorial plus t cube x cube by 3 factorial. This is the expansion for exponential e to the power x. So the expectation of e to the power tx therefore is 1 plus t into e to the power tx. Constant can come out of expectation. T square by 2 factorial ex square, t cube by 3 factorial ex cube, and so on. So now you see this ex is mean, okay, and ex square is variance. So these are what are called moments around the mean. Okay, so the first moment is the mean, second moment is variance, third moment I believe is called kurtosis, fourth moment is called skewness, and so on. So these are moments ex square, ex cube, etc., and nth moment is ex to the power n. Look at their coefficients. Okay, these coefficients are the expressions for those means, variances, kurtosis, skewness, etc. So let's understand this a little better. So if you take the derivative of moment generating function d dt of e to the power expectation of e to the power tx, mxt is nothing but expectation of e to the power tx. So this is equal to, you're differentiating with respect to t, so x becomes constant, so it becomes e to e x etx, ax expectation of x etx, and d2 dt square mxt is dt dt square, okay, or d square t e expectation of e to the power tx. This is equal to e x square e to the power tx. Okay, so these derivatives give us this expression. Now equate the first derivative to 0 with t equal to 0, not equate, take the value of t equal to 0 for the first derivative. This gives you expectation. Okay, and similarly make t equal to 0 in the second derivative. That gives you the variance. Okay, so you can get the mean and variance, the two most useful quantities for any random variable, by differentiating the moment generating function and equating it to 0. Okay, so that is the usefulness of moment generating function. You can get the mean and the variance from moment generating function. Okay, and the moments are mean variances, mean variance, kurtosis, skewness. These are called moments. Okay, about the mean. So, so by making t equal to 0 for the first derivative and for the second derivative, we can get mean and variance. And interestingly, they have connection with the coefficients of mean, variance, kurtosis, skewness in the expression for expansion of e to the power tx. Okay? So these correspondence we will look at once again. We have only about 5 to 6 minutes left. So let us complete that story of using the moment generating function and uniqueness theorems to prove that Sn star is standard normal. So let's find out the moment generating function of standard normal distribution. So the PDF for standard normal distribution is 1 by root 2 pi e to the power minus y square by 2. Mean is 0, standard deviation is 1. So sigma has become 1 and mu has become 0. So 1 by root 2 pi e to the power minus y square by 2 is the PDF for standard normal distribution. The moment generating function for this will be simply multiply by e to the power ty and do integration from minus infinity to plus infinity. So what we get is minus infinity to plus infinity integration 1 by root 2 pi e to the power minus y square by 2 plus ty. Okay, just adding the two exponents. Both are e to the power something. So when you do that, then we can do a bit of algebra here. We convert this to y square minus 2yt plus t square outside minus 1 by 2. And that I can do if I add t square by 2 to the expression. So I can isolate e to the power t square by 2. So now e to the power t square by 2 is constant because the integration is with respect to y. So I have minus infinity to plus infinity 1 by root 2 pi e to the power minus half y minus t square dy. So this is nothing but a normal distribution with mean as t, standard deviation as 1. And integration of a normal distribution, any normal distribution, is from minus infinity to plus infinity is 1. So the moment generating function for n01, that is standard normal distribution, is t square by 2. I hope it is visible. E to the power t square by 2. Okay, e to the power t square by 2, this expression. So can somebody verify that you are looking at MGF of n01? Can somebody verify? Yeah. Okay. So MGF of standard normal distribution is e to the power t square by 2. Very useful for us to remember. Okay. Then you can find out the mean by taking derivative with respect to t and equating t equal to 0. You can find out the you can verify that the standard deviation is 1 and the mean is 0 by taking the derivative of e to the power t square by 2 and making t equal to 0. Okay, this is what will come out to be. So for standard normal distribution, we have got the moment generating function as e to the power t square by 2. Now we have to prove central limit theorem. What is the moment generating function for Sn star, Sn minus n mu by sigma root n? So let's look at this. expectation of e to the power t Sn star, which is nothing but the MGF of the value Sn star, which we want to show as standard normal distributed. So this is expectation of e to the power t into Sn minus n mu divided by sigma root n, expansion of Sn star. This is nothing but e to the power I equal to 1 to n t into xi minus mu divided by sigma root n. Okay, so I'm just breaking n mu into n parts. Okay, so Sn minus so this Sn star is actually, sorry, it is xi. This is xi. Okay, this is xi. So this will be xi minus mu I going from 1 to n. So first x1 minus mu, then x2 minus mu, x3 minus mu, up to xn minus mu. Okay, look at the definition of Sn star. Oops. Sn star is Sn minus n mu, and Sn is nothing but x1 plus x2 up to xn minus n mu. So you distribute xn sigma xi I equal to 1 to n minus n mu. You give 1 mu to each of these xi's. Okay, if you give 1 mu to each of these xi's, then it will be e to the power I equal to 1 to n t xi minus mu divided by sigma root n. So when you do this algebra, you come to an expression expectation of e to the power t xi minus mu divided by sigma root n to the power n, because each random variable is identically distributed. Each has mean mu and standard deviation sigma. So you can take the product of all these and raise these to the power n, because each of these expression is same. Now this e to the power t xi minus n mu divided by sigma root n to the power n, you can expand e to the power this quantity by standard expansion of e to the power x. This is by Taylor expansion. And now you have expectation of 1 plus this quantity, and so on. And expectation distributes over the terms. Expectation of xi minus mu is 0. Okay, expectation of xi minus mu is 0, because it is the expectation of xi minus expectation of mu. Mu is constant. Expectation of xi is mu. Mu minus mu is 0. And this quantity again is the variance, which is 1. And now if you take it to the raise it to the look at the expression 1 plus t square by 2n and other expressions raised to the power n, and if you let n tends to infinity, then this expectation comes out to be e to the power t square by 2. In the next class we can do this derivation in more detail, applying theory of limits, applying L'Hospital rule and so on, and we will reach this conclusion that the moment generating function for Sn star is also e to the power t square by 2, which is same as the moment generating function of the standard normal distribution. So since these two expressions are identical, a moment generating function for standard normal distribution and moment generating function for Sn is identical, okay, is identical. Just a second, yeah. Since Sn star's moment generating function is e to the power t square by 2, and standard normal distribution's moment generating function is also t square by 2. Therefore, Sn star is normally distributed with mean 0 and standard deviation 1. Okay, so that is the proof of the central limit theorem. So from the top level, what are we getting out of this discussion? What is the gain? The gain is that take n random variables and let n be sufficiently large, then their sum is normally distributed, and you can construct a standard normal distribution out of that sum. And now you can make use of z-score table, okay, to build confidence intervals, 95% confidence interval, etc., which leads to test of hypothesis. Okay, so we are covering the ground in sheer steps, one by one milestones we are crossing, and central limit theorem now will allow us to do test of hypothesis based on this theory. Now, what is the correspondence between sampling and constructing this sum, x1, x2 up to xn? So this is something we would like to delve deeper in the next lecture. Why is this sum so important? After all, I'm taking sample after sample of corpus and seeing how many times NP gets expanded as DTNN. What has this got to do with computing the sum of n random variables, do not know their distribution, but able to make use of central limit theorem and say that this sum is normally distributed. And to be able to use z-score table, I convert it into standard normal form. What has this got to do with observing corpus, okay, and finding out how many times NP gets expanded as DTNN? What is that correspondence? So use of CLT in NLP is something we would like to do in the next lecture. So just summary of the discussion is that we first talked about parametric distribution and showed how by probability we can make word alignment correspondences. But in neural network-based machine translation, that correspondence is not obvious. Okay, it's non-parametric distribution. Then we want to have confidence in the probability values that we get for this alignment or probability value of a context-free grammar rule. We want to have confidence in that. So we learned some techniques. One is the z-score technique. The other is making use of z-score in getting values of some interesting quantities. And now building our grip on central limit theorem. And here is the main point, that if I take n random variables and sum them up, okay, if I take n random variables and sum them up, I get a normal distribution if n is larger. And I can get a standard normal distribution out of that sum and make use of instruments of normal distribution. Okay, so that connection we'll establish. So I'll stop here and see if there are questions. Are there questions?
One question which Nikhil asked was, what is T?
What is T? T is a variable. T doesn't have any significance. Okay, T is just a variable. So why somebody thought of moment generating function? Why is the moment generating function in that form? That is a very interesting question, and I think we should discuss this at some point of time.
Hello,
Yeah.
sir.
Yeah.
Sir, did you discuss that multinomial question? I just lost connection for a few minutes.
Multinomial. You mean the dice throwing and
Yeah,
NP?
yeah. So actually, my doubt was since we have dice and we have 6 outcomes. So in noun,
In noun phrases, there are 3 outcomes. Yes. I think I lost your connection, Manas. Yeah, I think the connection is lost. So what is T? And then is the distribution of NP going to DTN and NS, etc. is multinomial. And similarly for VP. Yes, that distribution is assumed to be multinomial. Okay, and that's why we get these values of the probability of NP going to DTNN as ratio of how many times NP gets expanded as DTNN and how many times overall, okay, because of this multinomial distribution. Okay, so I think I lost connection with Manas. Maybe we can discuss offline. Are there any other questions, points?
I have one doubt, like in statistical based machine translation, we have created a chart which has one-to-one mapping and which gives the probability for translation. But if there are there are some sentences like which have in one language we have a 6 words, but in other language we might have a 3 words or 4 words. So then how we prepare this chart?
So this is called fertility. So a nice example is advice in English going to Salah Dena in Hindi. So one word becoming 2 words in Hindi. This is called fertility. And you have contraction also. 2 words becoming a single word in the target side. So that is why phrase-based machine translation came in. So if you read the I believe the 4th chapter of my book, machine translation book,
Okay.
then I motivate how phrase-based machine translation became again inevitable. So word-to-word alignment is created by IBM 1 model through that expectation maximization algorithm, which I showed. Let me stop sharing. Okay, which I showed. Now what you do is that from word alignment, you build phrase alignments. Okay. Now phrase alignment does not really care about the length of the phrases. Okay? You can establish correspondences between variable length phrases also. So I advised him, मैंने उन्हें सलाह दिया. So advised him, उनको सलाह दिया. That correspondence will be established through what is called phrase alignment. And phrase alignment is a different algorithm, but it is founded on word alignment. Okay, you have to apply what is called union intersection algorithm. So that I discuss in my chapter 4 of the book. Also, it is given in Philip Cohen's book in machine translation.
Okay, sir.
Okay, so I guess we will stop now and meet 2 weeks later. Just leave with this question. What has this sum of random variables got to do with corpus collection and sample collection? Okay, what is that bridge? That we'll discuss next. Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.